In this video, we'll describe a very important problem in natural language processing, the problem of language modeling. So, a language model is a probabilistic model that assigns probabilities to any sequence of words. So it's a distribution essentially on sequences of words, on sentences, on documents. And so the problem of language modeling, or the task of language modeling, is to actually learn such a model that will assign high probabilities to well-formed sentences. So sentences that are likely to be written in some document or heard and so on. This is a problem or task that is very important in natural language processing. A lot of systems actually incorporate a language modeling component, such as speech recognition systems and machine translation systems. So, for instance, if we had a sentence we wanted to translate une personne intelligente, and we had a system that's pretty good at just translating each individual word. So, une would be, the system would know that you would translate it to which is here also, and personne would be translated by person, and then intelligente would be translated by smart. But imagine our system is also not so good at determining the order of these words. Then in this setting, language model would be very useful in distinguishing, for instance, whether we should prefer a person smart or a smart person as a good translation of une personne intelligente. And in particular, if we had a good language model, then it would recognize that this has a higher probability of being written by a person in English than a person smart. So in this case, it would have been able to reorder personne and put it after intelligent in the actual translation in English. So there are many other types of usage of language modeling and language problems. Language models. And so they're really, really important in natural language processing. An assumption that one often makes when someone designs a language model is to make the nth order Markov assumption. What this assumption says is that if we have a distribution, a probability distribution over a sequence, then then we're assuming that we can write it as the product of the probability of each element in the sequence, given only the n-1 previous elements in that sequence. So in our case, we're modeling words, so we're assuming that the word at position t is only dependent on the n-1 previous words and does not depend on the other words before that in the sequence of words, in the sentence or in the document. So this is a restrictive assumption. It essentially never really holds. It rarely holds, except for perhaps very, very large n values. And whenever I'm going to talk about context, I'm going to talk about these n-1 previous words, the words on which we're conditioning the probability of observing the next word. So the model or type of model that is very frequently used in natural language processing is known as the Engram model. So first, let's describe what we mean by Engram. An Engram is just a sequence of n words that usually we extract from some training data, from some corpus of words. So for instance, if we just take that sentence here as our corpus, our training data, then the unigrams that are contained is, there is, which is right here. There's there's sequence, and all the other individual words in that sentence. Examples of diagrams taken from that sentence would be is because we have is followed by here. Also a sequence, because we have followed by sequence here, and so on. And then trigrams, which corresponds to n equals 3, an engram for n equals 3. Well, an example is a sequence, because we have is a sequence here, a sequence of, because we have a sequence of here, and so on. So that's what an engram is, really, just a sequence of n words that is usually extracted from data. Remove some ink. And so an Engram model is going to estimate the conditional probability that we need in our Markov model for assigning the probability of a whole document or sentence. Is going to estimate that conditional probability based on counts of engrams, that counts that are extracted from some training corpus, some training data. So specifically, if we had a set of words, the n-1 previous words, so the context, and we're wondering what's the probability of some given word that is observed next, well, what we would do is that we would count. So imagine we have this function count that just contains the number of times that the context, so the word from position t minus 1, t minus n minus 1 up to t wt minus 1. So the number of times we observe this context followed by this word wt. So the probability, conditional probability, as modeled by, estimated by this model, is going to be proportional to that count. And then we're going to normalize that by the number of times we've seen this context followed by any word. So by dividing this way, then we're guaranteed that this estimate of the probability is a valid probability. It's going to sum to 1. Now, Engram models have one particular problem or challenge that they have to face, and it's the problem data sparsity. So if you want a good model that's accurate, that is close to reality, really what we want is n to be as large as possible. Otherwise, for instance, for n equals 1, then we're actually assuming that all the words are independent, because then the n minus 1 previous words, that's 1 minus 1, that's the 0 previous words. So we're conditioning on no words before any word for when we're modeling the probability of each word in the sentence. So effectively, we're considering that all the words are independent in the sequence, which is, of course, a very crude assumption to make. If we have n equals 2, then we're just assuming that if we know one word, then the distribution of the next word is not influenced by the third word before or fourth word before, and so on. So that again is a very crude approximation. So really we want n to be as large as possible to get a realistic model. However, for large values of n, then it means that when we're estimating these probabilities in this Engram model, it's going to be much more likely that for some new data in some testing corpora for which we're evaluating the probability of sentences, it's going to be much more likely that we will have never seen the exact context for which we have to condition for evaluating our conditional probabilities in the Engram model. And so there are ways of alleviating this problem. Essentially, there are all variants of this idea of smoothing the counts. That is, when we're, for instance, estimating the probability of some word given the 3 previous words, so we have 4gram here modeled, then instead of just making that proportional to the number of times we've seen W1 followed by W2 and W3 and then W4, and then normalizing, we actually have this probability be proportional to a combination of the count of seeing W1 up to next to W2, W3, and W4, and then combined with the number of times we've seen just W2 followed by W3, W4, and then combine that also with W3 and 4, and then just the number of times we've seen W4. And so there's a whole literature on ways of combining these different counts to get a model that doesn't overfit as much and generalizes better. But actually, as we'll see, this only partly solves the problem in the sense that there's something better we can do, and specifically we'll see a neural network language model that can outperform this approach.